All right, let's get going. February 3rd. Hope you guys had a good weekend. And I hope you're not Denver Broncos fans. 'Cause, that was ugly if you're a Denver Broncos fan. My Navy Reserve duty, every month I have to be in the Navy Reserve still. And my Navy Reserve duty is actually in Seattle. And so next week I'm headed up there. Actually, at the end of this week I'm headed up there. And I'm sure they'll probably still be celebrating that because that was a pretty big win for the Seahawks. And for those of you who care less about football, well, fine too. I didn't watch the game actually. But anyway. All right, so here's what we're going to do today. We're going to do a Unix tip of the day. Then we're going to talk about homework 2. Some of you guys actually found homework 2 online yesterday. I put it online kind of middle of the day yesterday and then was still tweaking it a little bit, but it should be good to go at this point. We'll talk about what homework 2 is going to entail and what that's going to be all about. And then I'll briefly mention Lab 2, which starts today as well. And the nice thing about Lab 2 is it's actually going to prepare you to do homework 2 for at least part of homework 2. So it's actually part of it's a little bit trickier than what you're going to have to do for homework 2, but it's going to be similar in that you'll be able to use what you do in Lab 2 to help out on homework 2. And then we're going to talk, I'll make a comment about reversing linked lists. In fact, I will start with that. I'll do that a little bit differently, or I'll start with that instead of the Unix tip of the day today. And then finally, we're going to go into this thing called recursion. OK, the Comp 50 people should be going, oh, yay, recursion. We know recursion really well. The Comp 11 people, I believe you talked a little bit about recursion in class. Did you guys go through a whole bunch of recursion examples in class? OK, we may be doing a bit of review in that sense then too. But that's all well and good. If it's review, and then we'll move on. OK, a thing about reversing linked lists. OK, this actually came up in the afternoon class the other day, but I thought I'd mention it here, just because I'll mention it there as well. But somebody brought up an interesting point. OK, remember I drew all those crazy arrows on the board to reverse a doubly linked list? Remember that, where we had links? And by the way, I forget who it was, but somebody in here gave me a great suggestion, which was to use colored chalk here. The colored chalk, I tried it in the second class. It actually didn't show up any better than the other chalk. But we're not going to do many linked lists in here today anyway. But if we're trying to reverse this linked list, in other words, we're trying to say that instead of the head being here and it going through the list this way, the head is now here, and we're going to make this one the head, and then everything in the middle is going to be the opposite way. In other words, this is the first element, the second element, the third element, the fourth element, fifth element, and then this is the tail. OK, you have to be really clever about how you actually go about changing those links to make it so that you still got a proper linked list when you've got it reversed. OK, somebody in the class the other day said, hey, wouldn't it be possible to go through the linked list in one direction, change all the links in that direction, and then go backwards through the linked list and change all the links going backwards in the other way? And my initial reaction was, OK, that's good. If you were doing an interview, you'd lose points because you have to go through the list twice. But that might be a way to do it. But then after the class, I realized there's a big problem with trying to do that. OK? If you're going through this list this way and trying to reverse, let's say you're going through the list and you're making all these guys point the other direction. What is the problem with doing that? If you tried to go through the whole list and then change all the ones that were this way to be reverse pointers? Yes? Yeah. Yeah. Yes, that's a good point. So what you're saying is if you're changing this one to be, if you're changing this pointer here, the previous pointer to be equal to this one like you were doing the reverse, then you'd be losing this pointer. Is that what you're saying? To get back the other way. If you change the top pointer to point to here, you mean? No? Right, that would be this one. You're saying you'd lose this one? Let's say you kept it. So if you were clever about it, you could keep this one in a temporary one, change this one, and then know to follow that one. So you could keep it temporarily. The problem, though, and this is what I thought you were getting at, is that if you go and you make this one point back this way, how are you going to follow the reverse links back to the first one? By doing it, you lose all those reverse links. And that was kind of the tricky part. So you'd have to somehow keep a big list of all those reverse links, and it doesn't seem to, it wouldn't really be the best idea. So you'd have a little bit of trouble doing that. Anyway, that's reversing a linked list. Both Lab 2 and Homework 2 will involve more linked lists, so you'll get lots of practice doing those. Okay? All right, let's go on to the Unix tip of the day. Here we go. This is, a couple different tips here especially for this homework assignment. This may come in very handy. A number of you in the first homework assignment, we didn't take any points off for this, at least we shouldn't have. But a number of you guys had output that didn't match what we were expecting in terms of the output. In other words, you had extra spaces at the end of your output, or you had other words like please input a number or something like that in the output. For this assignment, for assignment 3, I'm giving you an example. In fact, I'm giving you a text file that should match the output to your program. Okay, at least the test program that we give you. You should do your own tests in addition to that one. But I'm going to give you some output that is exactly like what the output for your program should actually be. Why is that good? Well, then you can compare the two for your program. Okay, you can actually compare the outputs, and you can see if the output that you created identically matches the output we've created. And then if it does, you're probably on the right track in terms of getting the data. Now, how do you actually go about doing those comparisons? There's 2 little tips here that I'm going to give you, and I want to show you what that is. Okay, so I have a couple of text files here. Now, one is called Jack and Jill, the other is called Jill and Jack.txt. Okay, and I hope you guys all know maybe you don't, but the nursery rhyme, Jack and Jill went up the hill to fetch a pail of water, et cetera, right? Well, in one of these, it's proper, and I'll show you what that is. Let's see. Let's see if we do less. I don't think it's even that big, but Jack and Jill, and there we go. Okay, Jack and Jill climbed up a hill to fetch a pail of water. Jack fell down and broke his crown, and Jill came tumbling after, and that's the end of it. Okay, I have swapped Jack and Jill in the other one. Okay, so if you do less, Jill and Jack, it's exactly the opposite. It doesn't rhyme anymore, but that's all right. Jill and Jack climbed up a stack, I don't know, to fetch a pail of water. Jill fell down and broke. Okay, so it's exactly the opposite, right? There's only one line in here which is actually the exact same in both, and that's this one. Okay, what you can do is you can use this command called diff, D-I-F-F, to actually compare those two. And unfortunately, I say unfortunately, it's the output of diff is understandable, but takes a little while to actually understand. But the big thing you can use it for is just to say, hey, are my 2 files different? And then it will point you in the right direction, but some of the messages are different. So let me show you what this actually looks like. Okay, you can just type diff Jack and Jill, and then Jill and Jack, like that. Okay, and what comes out is this funny-looking report here, but it says, look, Jack and Jill climbed up a hill is different than Jill and Jack climbed up a hill, right? That happens to be on line 1. Okay, and then down here, it's these 2 lines, Jack fell down and broke his crown and Jill came tumbling after, are different than Jill fell down and broke her crown and Jack came tumbling after. Now, can you see how it might be important to see the differences between your output and the output that we give you, right? So that's the way we can do that. You can also, there's also some other ways you can call this. If I do diff -u and then Jack and Jill and Jack, it's a similar type of format here, but it actually tells you here's the line that one file had, here's the differing line in the other file. Okay, and it does that. It just tells you where the differences are. Okay, and if you want to figure out how it actually does what all these pluses and minuses mean and all the numbers, you can go ahead and look into that. But I don't think that's quite as important as just being able to run this file, run this command and say, hey, my files are different. Okay, that's the bottom line on that command. Now, the question is, how do you actually get your output from your program to produce a file that you can use in this diff command? Well, it's as easy as using the greater than symbol. Okay? Here's what it would be. So let me see if I can do this. Let's see. If I go to a previous day, let's go to day 4. And let's hope that I have here. Nope, I don't actually have it in here. If I was to, let's say, I don't have an actual file in here. Yes, here, we'll do this. Nano, which I'll create a new file, test file.cpp. Let's see. Number encoding in live is difficult. IO stream, and then using namespace, std, int main, cout, hello, oops, cout, hello world, like that. Return 0. I hope I got that right. Have you seen any errors quickly? OK, looks good. Yes, test file. OK, make test file. You can just make. By the way, you don't need a make file if you just have one program. It knows how to go, oh, I can find that file if you just type that. Anyway, it's test file. So if I type test file, like /test file to run my program, right, it's going to do hello world. If I do /test file with a greater than sign into something like test output.txt, it looks like it didn't run. But guess what? In the file test output is the output from your file. So if we do less test output, there's the output. And then you've got it in the file. OK, so that's kind of nice that if you run your program, use that greater than sign to what we call pipe it into a file, right, as if you were pouring into a pipe into the file, right, then you will get the output, and then you can use that diff command to do it, to compare the two outputs. Questions on that? Don't try to do it into the same file. Then you lose the file. You can always copy it over again, but don't, like, in other words, don't try to output it into the same file that you're going to compare it against. That would not work well. OK. Questions on that? Awesome. OK. Oops. There we go. OK. So the next homework assignment, which is on the website today and is you can take a look at it. I didn't print it out. It's like a 5-page write-up to like tell you how to do some of these things. Most of it's like code and stuff that it's giving you some instructions on. Here's what it is. So the other day, I mentioned the idea of a calendar program that your phone might have, or Google Calendar, or the Android or iPhone calendar, something. OK? We're going to start to build up a little program that does these calendar functions for us. OK? We actually are going to build a little kind of a calendar. And the fun part about it is that at the end, we're going to be able to export it into your own Google Calendar if you have one, or import it from your Google Calendar into your program, which would be kind of fun. OK? And it's just going to be this calendar appointment application. In order to have a calendar, okay, you need to set up your day, okay, into some form, okay, where you've got these things we're going to call events in them. Okay, it's just going to be events. Okay, and you're going to have an event, and let's say you have, let's say your first event is, oh, I don't know, you get up in the morning and you work out, right? Because everybody works out in here, right? You work out, and you work out from 0800 to 0900. Okay, and then let's say that that's one of your events, and then later during the day you've got lunch, right? And you've got lunch, and lunch we'll put right here, and lunch would be from like 1200 to I'm gonna use 24-hour time in this sense. In other words, 0 is midnight, 12 is noon, 13 is 1 p.m., 14 is 2 p.m., and all that up to 24. Okay, we're going to do that so it makes it a lot easier to actually do these comparisons. So let's say you eat lunch from 1200 to 1300. Okay, there's a couple different events in there. Okay, and then let's say you want to put another event in there, which is, oh, I don't know, data structures class, right? if we have another event in data structures class, it's going to go right in the middle because data structures class happens to be from 10:30 to 11:45, right? And so we're going to have our data structures class, and we've got to fit it in here somewhere in this order. We can't do what we've been doing in the past, which is just throwing items into some list in whatever order they actually appear in. Okay, we're going to have to do some computation to figure out where in the list that is, so that we have this thing called an ordered list. Okay, so if we had data structures class, right, we're going to put it right there. We're not going to put it above or below. We're going to put it right where it belongs. Okay, meaning that we're going to have to keep this order for this ordered list. Okay, having an ordered list, we say that the invariant of that list is that it's always sorted in a particular order. Okay, so we say that. And this is a term we will use a lot in class. Okay, we say, hey, the invariant to this list is that it is in order all the time. Okay, later we'll deal with lists that are out of order, and then we're going to try to actually sort them. Okay, we're going to actually put them in order. But our list will always be in order when we get the list and when we actually, after we get done doing something to the list. Okay, that's going to be our invariant. Okay, so that's kind of the idea of what we're going to be doing. Let me go through a couple more details here. Okay. I said that we're going to have these things called events. Okay, we're going to have an event class, okay? And that class is going to have only a few private members, actually. It's going to have a start time, an end time, and a description. Okay, so it could be 10:30 would be the start time, 11:45 would be the end time, and data structures would be the description. Okay? And we're going to sort this. We're going to keep this order only by start time. So sometimes in your calendar you have events that overlap. Like you create a whole day-long event for something, and then you have another event that starts in the middle of the day. And sometimes you have these overlap. We are not going to worry about the overlap part of it. All we're going to worry about for this assignment is the start time. Okay, so in this case, workouts before data structures before lunch. And if data structure or if lunch happened to start at 11:30, like you pull out a sandwich in the middle of class or something, right? We don't care. All we care about is that the data structure started before lunch starts. Make sense? Okay, yes?
If two things start at the same time, does it matter which comes first?
Good question. If two things start at the same time, does it matter which comes first? Yes, in that when you insert into a list, we're going to, and this is only by, we just decided this. This is not any reason for this other than we want it to be so that your program looks like everybody else's, does the same thing. If you insert something into a list and they have the same start time, the one you insert should be after the one that's already in there. That's the bottom line to that. Okay? All right. So everybody gets the idea of what an event is. This is not a pointer. It's just a class, right? We'll get to what we do with events and how we make them behave like pointers in a few minutes. Okay? But this is an event class that we're going to use. All right. The events are going to have standard getters and setters, just like most classes that we build. And then they're going to have a couple of other methods. Okay? There's going to be a method called am I before, and you're going to pass in some other event. So let's say we passed in, let's say data structures is the event we're looking at, right? And we said data structures, am I before lunch? It would return true. Okay? So you're going to have to build that functionality into that. Am I before lunch? If you said lunch, am I before data structures? It would be false. Good? All right. There's another one here which sounds like it could be kind of wrapped into am I before, but it's definitely different. Take a look at this one. This one we're calling is same event as another event. In other words, if you have some event, right, and you have some event we could call something like temp event, right? And temp event started at 10:30 and finished at 11:45 and was called data structures, right? Is that event the same as our data structures event? We need to check that. Okay, and that's what this method is going to do. Same thing, you pass in some other event and you check and see if it's the same as event. How are we going to check and see if data structures is the same as this temporary event? Relatively simple. There we go, compare all the fields. You'll say, look, is the start time for data structure the start time as our temp? Is the end time the same? And is the description the same? Good. Okay, so that's what we're going to do in this one. Another one is going to be print event. Now, print event is relatively straightforward. It's going to say something like start time, and then a little colon, and then say might say 10:30, and then underneath, and then it's going to be a new line, and it's going to say end time, and it's going to say 11:45, and then it's going to say description, and then it's going to say description. It's going to say data structures, something like that. Okay, that's all your print event does. Okay? And then there's this weird one. It returns a string, and it's called event CSV. Anybody know what CSV stands for? Comma separated values in general. Okay, is what we do at CSV. It could be variables, I guess, but in this case, comma separated values. Did you guys use those in Comp 11 at all? I doubt you would have. Okay, a comma separated value is simply, in this case anyway, our start time, comma, our end time, comma, the description. So our event CSV function, which, by the way, we've already built for you, so you don't even have to worry about that, but I'm just going to show you what it is because we'll use it later. In this case, it's going to be 10:30, comma, 11:45, comma, data structures, like that. That's going to be a comma separated value list. What's the problem with this if we do it just like this? What might be there? What might one problem be with that? Any ideas? It's not the biggest deal in this case, but what if we put a comma in our description? Wouldn't that mean it would be a comma? Because comma here is what is going to tell us where the dividing line is between all of our little fields. That's what it's for. And OK, the bigger question is, why do we even care about this? Why do I care about this comma separated value thing? When one computer talks to another computer, OK, we've talked about this before. When one computer talks to another computer, they need some way to pass data back and forth. One standard method for passing data back and forth is through the use of this comma separated value. Okay? So you might pass an event to, say, Google Calendar or something. And by the way, they do it. They're a little more sneaky in the way they do it, but the idea is the same. They might say, hey, Google Calendar might say, hey, I want an event. You're going to pass an event in, and it's going to expect a comma separated value, where the first part before the comma is the start time, the next one after the first comma is the end time, and the final one is the description. Okay? And you're going to have to be able to do that. Now, as I said, we've already built this for you for this assignment, but we'll see those again, especially when you get into talking between computers. You're going to need to know those sorts of things. Okay? Questions on those? All right. That's the event class for the homework. All right. We are also going to have not just an event, we're going to have a day, like February 3rd, right? We are not going to worry about, for this assignment, more than one day. In fact, we're not even going to name the day. We're just going to have a day. Okay? But a day is also going to be a class. Okay? And these are the following methods for the class. You're going to have to schedule an event, and there's 3 of those here. Okay? What this means is that you can schedule an event in 3 different ways. It's kind of like having different constructors. You can overload regular old methods as well as destructors, meaning you can call this method with no parameters, or you can call this method with a start time and an end time and a description, or you can call it with some other event. Okay, so let's say you already created an event. You can pass that event into the schedule event, and then it will schedule the event during your day. Okay? That's the one method that this is going to, your day is going to be able to do. Another method, cancel event, right? Let's say that you were so confused in data structures class, you decided to skip lunch and go straight to the lab, right? Well, you'd cancel this event, right? You'd cancel your lunch event, and you have to be able to do that. Well, what does that mean? That means we're going to remove it from our list. Okay? And if we're doing that, we have to be clever about removing it from the list so that the list is still a proper list. Okay? Then we have to print the day. Printing the day is actually really easy, right? We already know how to print an event. So printing a day is just what? Going through the list, saying print each day, or print each event. Sorry, print each event during the day. Easy enough to do. Okay? And then finally, we're going to have this export day. And export day is going to be a list, or a file, or not even a file, a big long string that has a comma-separated value, and then on the next line, it's got another comma-separated value list of, let's say, lunch, all the way down your day. Okay? And if you're going to pass, say, the whole list to Google Calendar or something like that, you would do it this way. So that's all we're going to have to be able to do. Schedule event, cancel event, print day, and export day. Then, of course, we're going to have a destructor in there. Okay? All right. Questions on what a day does or what an event does? No? OK. I already mentioned this. We've got an event class. Now, for this assignment, we have been talking about two types of lists in here, right? We've been talking about dynamic arrays and linked lists. This assignment is going to involve creating two versions of the day class. One is going to be a dynamic array version, and the other is going to be a singly linked list. So no need to worry about these doubly linked lists. You'll get enough of that in lab. Okay? And both day implementations will be completely interchangeable from the perspective of the main function and from the perspective of using the event. In other words, you don't need to change the event at all, and you don't need to change your main function at all in order to use either the linked list operation or linked list version of day or the dynamic array version of day. Okay, how do we go about doing that? Well, it all has to do with when you compile the program, which one of the day classes you actually pass into the compiler. It will gladly use either one and to link up to your main.cpp file. Okay, so it's going to be relatively like it's and the reason we're doing that is twofold. Number one, to give you practice doing dynamic arrays and linked lists, and number two, to say, hey, look what you can do. You can have multiple implementations of the same exact function, okay, and you can link them separately. Okay, in some sense, it's similar to each one of you guys has the same main function for the program 1 for homework 1, and if we could all take, I could take your individual what was it that we did? Your individual rectangle functions and place them in with our main function, and it should work. So it's kind of the same idea. But in this case, you're going to do two different implementations. Okay? All right. So a couple other things we're going to talk about on this. I noticed this on the last homework, or sorry, the last lab in particular. Okay? And it's cropped up a little bit in some of the homeworks as well. There is a difference between when to use this dot operator to talk about the method of some class, to actually access the method of a class, versus this funny-looking pointer operator, which is actually a dash and then a greater than sign. Okay? And what this refers to is whether or not you are using a pointer or just an object in general. Okay? And you've all seen this before, I'm sure, but just to refresh your memory on this a little bit. If you have an object, okay, and it's not a pointer, okay, it seems like a strange way to say it, but if it's an object that's not a pointer, okay, the members of that object are accessed by saying n.member. Okay, I'll show you an example in a minute. If it is a pointer, you use p arrow dash greater than and member, and that refers to the member. Okay? Here's what it's actually doing under the covers. Okay? It's actually saying to the pointer, give me the class or the object you're talking about. Go to the memory location and find that object, and then give me that member. Okay? So this is dereferencing that pointer and then saying dot member. And this is you could interchange anytime you see a pointer arrow member. You could do this every time. You'd have to remember the parentheses, but you could do it, and it would work out fine. But it's easier and clearer, and kind of tells you, hey, this is a pointer to something, to do it this way. Okay? Let me show you the examples from, let's say, our homework this week. Let's say you have a breakfast event, right? Let's say you have that breakfast event, and you set it up like this. Event breakfast equals event, and then you put in the constructor, your times and your description. Okay? If you've got this, what you're doing is you're saying this is not a pointer, it's actually an object. Okay? The compiler sets up space for that object, and this is actually just the object itself. You would refer to the get start time, or rather the start time. Okay? I think it should be called get start time, probably the way you've done it. But you would be breakfast dot, in our case, get start time. Okay? See how that works for the non-pointers? And then pointers looks like this. Okay? So let's say you start a new event like this, and you say new event like this. Okay? The new command says, hey, I'm going to expect a pointer back to this. The new command goes to the operating system and says, hey, give me the memory for this. Okay? Just like all of our dynamic systems, our dynamic arrays and so forth. And then now we've got a pointer, and now new event has to be like this. New event get start time or start time with the little arrow pointer. Okay? You may get those confused. The nice thing is the compiler is pretty good about telling you, hey, this should be one or the other. Clang is pretty good about that. So most of the time it might give you some error, but it'll point right here and say, hey, I don't understand what that is. Okay? And you'll change it because you'll go, oh, it's not really a pointer, or whatever. Okay. Questions on that one? Okay. Good. All right. Before we go into recursion, the lab, as I said, starts today. The lab is going to be, you're going to have to work with doubly linked lists on the lab. Okay, the doubly linked list that we had up there before. Okay, the lab leaders, okay, are going to go through some examples of this, and what you're going to have to do is like insert into a doubly linked list, right? You're going to have to insert into a doubly linked list. Like let's say you want to insert right here. Well, you've got to make the proper pointer changes, and you've also got to make sure that your head and your tail are pointing to the right place as well. Okay, so there's a couple different things. Now, one of the nice things about the lab is, remember in class we did I think we did insert after in class, where we kind of went through an example of that. Go back to the video if you want to check it out again. We did an insert after. That function is going to be written for you in the lab. You have to write the insert before, or maybe it's the other way around, I forget. But either way, you have to actually do that and write the function to do that. A big tip would be look at how the insert after one works and rearrange the insert before, like write the insert before to do the same sort of thing, but take into consideration you've got to think about slightly different way to do it. You can use it as a guide, and instead of just actually writing, like trying to write it from scratch. Okay, that's my big tip of the day for the lab. Okay. All right, I think you'll do fine on that. Okay, all right. So, recursion. Okay, recursion. You guys have, if you've heard of this before, you'll kind of get this little joke up here. Okay, actually there's two jokes in here. All right, the recursion. Okay, this is the joke. To understand recursion, you must understand recursion. Well, what does that mean? Well, recursion is all about self-referencing things. Okay, so something will refer to itself in order to get some job done. Okay, it's a mathematical term. You might deal with it in math, but we'll deal with it in computer science. What it's going to mean is we're going to actually call a function from itself. Okay, and again, if you've seen it before, this is a review, and that's great. Google plays a little joke, right? If you type in recursion into Google, it will say, "Did you mean recursion?" Right? And you go, "Oh yeah, I did," and you click on it, and then it brings you back to the same page and says, "Did you mean recursion?" Right? So it's kind of sneaky that way. But they're playing on this computer science joke, right? That recursion is all about self-referencing what you're working on. Okay. And in fact, if you look at the definition from Wikipedia that comes up, recursion is a process of repeating items in a self-similar way. For instance, when the surface of two mirrors are parallel with each other, blah, blah, blah. You guys have all gone somewhere where there's a mirror behind you and a mirror in front of you, and you look into one mirror, and it's like mirror, 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 and you always kind of try to find the last one, right? But the last one doesn't really exist because it just keeps on going forever. It's because the light's bouncing back and forth between the two mirrors and creating a smaller and smaller version in both mirrors of the situation, right? That's, in some sense, recursion. Okay? It's like using the mirror to see a picture, to do a reflection of a mirror, of the same mirror, blah, blah, blah. Okay? That's what recursion's, kind of the bottom line on recursion. Okay. Recursion is not some magical thing. Okay? If you did get through Comp 11, you're like, wow, that recursion was really crazy. I never understood it, and it was very sneaky. It's not that bad. okay, when you talk about it. There's nothing really sneaky about it. Okay? It basically means that a function will call itself. Okay? You could write a function that looks like this. Int main, right? This would be a terrible idea. Okay? Basically because it would be exactly like that mirror problem, right? What this means is the program starts and it goes to main, and then it says main. And that goes, oh, okay, I'm going to call this one up here. I'm going to start over and call here. And then it goes down and then it says, oh, call main. Oh, okay, I'm going to do, then the program will very gladly keep doing this. Okay, and it will keep doing this until it actually most likely segfaults. Okay? And the reason it's going to segfault is because when you're calling another function, you've basically got to save the state of the computer when you do that calling of the function. Okay? So what do I mean by that? All right, pretend we live in a world where computers only have one processor. Okay, this is kind of important in this sense. And it just, what it means is you're like dual or quad core computers. We're not kind of talking about that idea right now because you can do some sneaky things with that. But if you are a program and you get to some, and you're running through the program and you get to some function call, okay, you can't do two things at once. And you need to, when you go to that function call and call some other function, you basically have to say, wait a sec, I need to save what I'm doing right now, save all the state, all my variables, save all the stuff, not quite that detailed, but you have to save that, and then you can go and call the other function. And the other function can run, blah, blah, blah. And when it returns to your original one, the original function has to say, OK, where was I when I started all this? Right? What happened? Where was I when I started this? OK, let me re-put the pieces back together and go from there. It's exactly what's happening when you do a recursive call of calling itself. Main will start this main function, and it will have to save all the stuff, and then it will call another one and save all the stuff, and call another one and save all the state, and eventually it runs out of memory. Okay, and it's actually not it doesn't take that long to actually run out of memory in general. But this is just to show you what's really, what the bottom line recursion could mean. Okay, all right. In real life, we don't see too many examples of recursion, like the way we tell people to do stuff, but this is a kind of one of the examples that I came up with here. Let's say you're trying to tell someone how to solve a jigsaw puzzle, but you want to do it recursively. Okay? This would be a terrible way to tell somebody to do it. But first thing you might say, okay, you're going to solve the puzzle. Okay, here's your steps to solve the puzzle. All right, step 1, is the puzzle finished? If it is, you stop, right? You've solved it. Stop. If the puzzle isn't finished, find the correct puzzle piece and put it in the right place. Step 3, solve the puzzle, right? Well, what this means is now you've got a puzzle piece and you've placed it in the right place, and obviously the devil's in the details there because puzzles don't really work that way, but you do it, right? And then you're going to say solve the puzzle, and you're going to go, okay, I'm going to start over again. Solve the puzzle. Is the puzzle finished? No. Find a correct piece and place it. Okay, boom, I placed a correct piece. Solve the puzzle, right? You see how this is a recursive command. Recursion in a lot of ways looks a lot like loops, in that you're doing one thing over and over and over again, and it is very similar to loops. In fact, the dirty little secret is you can always change a recursion into a loop if you really want to, but that sometimes also makes your program harder to understand. Okay, we'll get into some recursion that actually is very beautiful and very easy to understand in some cases. Okay, everybody get the idea of the what's going on here with this example? Not too bad. Okay. All right. Here's another horrible example. I'm giving lots of horrible examples today, right? Here's another horrible one. Okay, so this is an actual program, right? We could say recurse, and then we could pass in this value called how many. Okay. And what it's going to do is it's going to print out that number, and then it's going to call itself with that number plus 1. Okay? And it's going to do that, and then it's going to print out that number plus 1, and it's print out that number plus 1, plus 1, plus 1, plus 1. And if we started with 0, right, we're going to do this, and then this also will probably crash. Okay? Let me show you how quickly it actually crashes. We can do it here. Let's see. Day 5, recursion. Recurse count up forever. Okay, so it's count, there it goes. Right? It ended up getting up to 262,021 on my computer here. Okay, and it segfaulted. But what did it do? It started 0, and it counted up and counted up and counted up. And remember, each time it counted, like each time it called itself, what happened was it had to save that state and then got to call itself. And doing that wasted memory, well, took up memory until it got to 262,000 and said, I'm done. I'm out of memory for this problem here. The amount of memory I was given, I don't have any more, and I'm done. Okay? Segfaults. Compilers, by the way, are clever these days. If you used a compiler flag that said, hey, do this make this into a fast, small program that's efficient, the computer would say, OK, actually, it might not with this one. This one it might not. But in many, well, no, that's not true. In this one it would. It would be able to say, I'm going to turn this into a loop and forget about all that silly recursion. OK, the compiler will actually do that, at least Clang will. And then it would go on until you run out of, until the number gets too big, and then it might wrap around or whatever. But it wouldn't do this recursion call itself, which is nice because what that means is that you can write a nice, pretty function, and the compiler will unravel it for you and do it the way that it probably should be best for the computer. OK, so that's kind of the bottom line there.
Well, what's the flag for the small?
If you do -big O, and then S, that will give you a small, fast program, actually. Okay? There's other ones. A lot of times you'll see -O3, which is also kind of similar. That it tries to do a lot of optimizations, exactly like this, to make your program run faster. Okay? In here, we actually had I think we had the -O3 on the last program. If you want to use DDD or some other debugger, you definitely don't want to use this because all those optimizations make it so that the debugger can't really figure out what's going on in your original code, and it's bad. What you'd want to do is replace this with -G, which says, hey, give me more information about my program so that I can actually debug it. Okay, so you wouldn't want to use that if you were debugging a program. Okay, but if you're writing a program and you end up wanting to deliver it to people for real, you'll absolutely want to do this because then you'll get a nice, fast, small program that's been optimized by the compiler. OK? All right. Any other questions on that? OK. Let's stop with these silly examples. Let's talk about another example of how we could use recursion to solve a problem. OK? Let's say we want to count down recursively from some number n down to 0. OK? Here's the algorithm that we're going to use to do it. OK? We're going to pass in this number n, and then we're going to say, first we're going to say, is n less than 0? Because we're counting all the way down to 0. If n is less than 0, stop. You're done. Otherwise, say n. Okay? Or in our case, print out n if we're doing a program. And then count down from n minus 1. Okay? One of the things about recursion that you're trying to do is you're trying to break the problem into slightly smaller problems. Okay, in this case, we're trying to count down from some number down to 0. Okay, and we're going to start with this number. And then the slightly smaller part of that problem is saying, hey, now we're going to count down from n minus 1. Okay, so the algorithm for this would be if we're counting down from 3, right? OK, count down from 3. Is 3 less than 0? No. So we say 3. Count down from 3 minus 1 is now 2, so 2. So we're going to count down from 2, and we're going to go back up, and we're going to start over. Is n less than 0? 2 is less than 0, so we're not going to stop, so we're going to say 2. Count down from 1. Do it again. Is less than 0? No. 1. Say n. Count down from 0. Is n less than 0? No. Say 0. 0. Count down from -1. Is n less than 0? It is. Stop. That's the whole recursion. Okay? Pretty like straightforward stuff. And most of you guys have probably seen this program before. Okay? Here's the program, how to count down with recursion. Okay? What we're doing is we're doing exactly what that little algorithm said. Okay? Here's the function, countdown. Okay? And it's going to count down. It's going to say is count less than 0, just return. Otherwise, print out the number, count, and then a new line. And then count down from count minus 1. Okay? That's all it's going to do. So if we're going to go from, let me write down the actual function calls that happen here. Okay? Let's say we're going to count down from 3. We're going to go count down 3. Okay? And 3 is going to go through it. It's going to say, I'm not less than 0. I'm going to print out 3. So 3 is going to get printed out. And then it's going to count down, count minus 1. So this is going to now call count down 2. Okay? It's going to go through the loop here. It's going to say, or it's going to go through the statements here. It's going to say, is count less than 0? No. Print out 2. Right? And then this one is going to call count down. You guys get the picture, I hope, at this point. 1. And then that one's going to go count down 0. And then 0 is actually going to also go count down -1. And -1 is going to return. So it's going to go boom, boom, boom. It's going to write down 1, 0, and then this is going to return. It's going to return control to this program, or this function. It's going to return control to this one. It's going to return control to this one. It's going to return control to this one, return control to this one. And then this one is going to end, and it's going to go back to where it was called at the beginning. This is countdown 10. But do you see the idea of how you've got these things cascading down, kind of like that mirror thing? Okay, you get that idea? All right. That's how you can count down recursively. How might you count up recursively? Okay, how might you count up recursively? This one's a little trickier. When you're counting down to 0, what is the case where you stop? Did I have that on the last one, the base case? Yeah. The base case where you stopped for counting down is 0. Right? You're counting down, and you go da-da-da-da-da, and I'm 0. If I'm starting from 100 and counting down, I'm going to stop at 0. If I'm starting from 1,000,000 and counting down, I'm going to stop at 0. That makes it easy. This base case is always necessary in these recursive programs, okay? Because you need to know when to stop. If we're counting up, on the other hand, when do we know how to stop? If you're counting from 0 to 100, you stop at 100. If you're counting from 0 to 1,000,000, you stop at 1,000,000. If you're counting from 0 to 2,000,000, you stop at 2,000,000, which means that you don't have a common base case. Okay? So you're going to need to think about these things when you do this. Turns out that because of this whole cascading business, we can modify one line in this program, actually not even modify it, swap one line in this program to a different part of the program and actually count up appropriately. Ideas how we might do that? Take a look. Take a second to look at this. See which line we might want to change so that we can actually print the numbers up instead of down. We don't need to change any details. We just swap a line in here. One sec. A couple people. Let everybody take a look at it for a minute. Okay. If you're not getting it, that's OK. This will be hopefully an illuminating moment in a sec. Yes, what was your answer to this one?
Swap the cout line with the line that follows it.
If you swap those two lines, in fact, I think I actually do that. Right, there we go. If you swap those two lines, let's see what happens. Okay? I changed a couple things. First of all, I said count up instead of down. You didn't need to. I mean, it's going to do the same thing. But I changed this to count up. That's all I did, all the change I made. I didn't actually, that could still say count down, it would still count up in this case. We swapped these two things, okay? Because let's go through what's happening here. Instead of downs, these are all now going to be ups, right? Count up, 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 and up, okay? All right, let's look through what's going on here. All right, we count up. If count is less than 0, so we're going to do from 3 again. If count is less than 0, return. We're not. Count up, count minus 1. Have we printed anything yet? Aha! We haven't printed anything yet. So now we're still waiting around. Okay? We're still waiting around. We've gone to count up 2. And we're going to follow this. We're going to say, is count less than 0? No. Count up 1. We still haven't printed anything. Count up 0, and then count up -1. When we get to count up -1, we still haven't printed anything yet. Okay? All this is being stored in that state we were kind of talking about before. Okay? I mean, it's not even that. It's just that this line, we never get to this line in any of those functions because we're always going and doing the recursive call before we actually get there. Okay? Well, what happens is we get to -1 over here, and we say, OK, we're done. Well, we return to the 0, 1. And the 0, 1, it just finished counting at -1. Then it prints 0. OK? Then it prints 0. And then it ends. And it goes back to the one that called it, which happened to be count up 1. And count up 1 just finished doing count up 0. And it gets to here and says, oh, I'm going to print 1. Ta-da! Right? And the same thing with count up 2. It's going to be done with count up 1, so it's going to do 2, 2. And then 3 does the same thing and then ends. OK? So do you see how we kind of reversed the idea of where we were doing the counting? We're actually waiting to print everything out until we get all the way through there, and then the last one prints, then this one, then this one, then this one, then this one. OK? That was kind of clever, where we were able to change the idea of when we print it out just by swapping those two lines. OK? Question? Is there a speed difference? Good question. Depends what you mean by speed difference. The number of operations here is going to be exactly the same. So no, there won't be any speed difference in that sense. Okay? In some sense, what you're going to do is you're going to, at the end of this, you're going to spit out all the numbers. You're going to 0 through 10, right? Because that's going to be return, 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 return. Print out. That's the only difference there. Okay? The other one, it prints the number, then it goes and calls the function. That takes some time. Then it prints another one. It takes some time. But otherwise, the overall time should not be significantly different in that sense.
Okay, so the first one will print at regular intervals, and this one will.
Yeah, that's exactly right. The first one prints at regular intervals. This one prints out kind of all at once. I mean, there is the return that takes some time too. But yeah, it's not quite as much logic to print out. Yeah. All right. Any other questions on that? Yes? No, is this the most efficient way to count up? Good question. The most efficient way to count up is a simple loop. Okay? Why? Because we're doing all this calling of other functions, and that actually takes time. Yeah. The reason, that's a very good question. The reason I'm showing you recursion for these simple examples is because they're simple examples, not because they're particularly efficient. Yeah. I mean, if you wrote a count up function like this, somebody would go, oh, that's clever, but not particularly good in that sense. Yeah, very good question. All right, other questions on this? OK. Let's look at some other common functions. OK, some other common recursion functions. OK, and we're not going to do any more slides on this one now. There are lots of different, and by the way, one of the reasons that we're showing recursion at all is not for the simple cases, but to kind of build up to some of these harder cases that are more efficient, or not necessarily more efficient, but easier to understand when you're programming them. And that's really the difference. Remember, the compiler will pretty much try to get rid of the recursive calls if it can, because they're not really that efficient. OK. All right. So let's say we wanted to calculate the power, one number raised to some other number. OK? Can we do this recursively? Well, let's see what we're talking about here. OK? If we want to look at the power of a number, in other words, b raised to the n power. OK? What does that mean? Well, you guys all know what this means, right? That means b times b times b dot 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 b, where this amount, OK, is n. OK? That's just how many times it does this. OK? And the nice thing about this is this can actually be rewritten. Okay? It can be rewritten like this. B to the n equals b times b times b times b times b times b dot dot dot, where this number is now just n minus 1. See how we've kind of broken it down into a slightly simpler problem, just like we did before? Okay? B times the power of b to the n minus 1. Okay? What does that actually mean? How can we write this in a little more mathy terms? B to the n, okay, equals, that was a terrible curly bracket. How's that? That's a little better. All right. So b to the n, okay, we could write the following. Okay? We could say it equals b times b to the n minus 1 if, when is this true? If what? If n is greater than 0, right? N is greater than 0. Okay, if we've got all these, while we don't have any more b, or while we still got b's, we can say that the power b raised to the power of n is b times b n minus 1 if n is greater than 0. And if n equals 0, okay, like that. Okay, that's because anything raised to the 0th power is just 1. Okay, so there's our way of describing our function. And this nice little recursive bit in here is the part where it says, we've got a slightly smaller problem. And by the way, we have a base case. Okay, so now we've got that. Okay, we can just say, let's write our little function. Okay, let's write our little power function in here. Okay, so we have, okay, let's do it this way. Let's say that power, let's say we're going to use, let's say that b can actually be, it can be any type of number, right? It can be an integer or a floating point value. Okay? And in this case, we couldn't use non-floating point or non-integer values for this sort of recursion. Okay? If you want to take like 2 to the 1.6, right? You've got to use some other numerical methods to do that. You're not going to want to do that just with this method. You're not going to be able to have any base case where it's going to work out correctly. Okay, but in this case, we can do this. We can say that if b is a floating point value, let's call it a double, right? A floating point value with lots of precision. Okay, double. Okay, we'll call this power. Okay, and we'll have, let's say, another double for the b, which is like that, and an integer value for our n, like that. I'm really bad at these. There we go. Well, better. OK, so this is good. What this is going to say is do our power function and then return a double value to us. OK? All right. Well, let's just follow this construction that we have, almost identical to, or almost exactly like this, right? If n is equal to 0, or you could say less than 0, but you'd probably want an assert on there because you can't do powers of, well, you can't do powers in this way of negatives either. But if n equals 0, okay, we are going to return 1. Okay? All right. Otherwise, or else, we don't actually even need an else in there because this is going to return, so we don't even need an else in there. We could write it if we want to. Or we can just write return, right? Return b times power of n minus 1. And did I do that wrong? Oh, thank you. Power of b, comma, n minus 1. How's that? Thank you. All right. So now we've got our recursive function here. And each time it returns, now we're going to have to use that return value and multiply it by what the current value is. Okay? So let's take a look at an example of this. Let's do power of 2 raised to the 3rd power. Okay? Let's see what happens on this. All right? What happens is we start out and we say, OK, power 2 of 3. Is n equal to 0? No, it's not. OK? So return b times the power of b n minus 1. So this is going to return b times power of 2, like that. Okay, that's what this one's returning. Okay? Then we're going to get to this one, and this is going to recall that power function, and it's going to go through the question of whether it's equal to 0, whether n equals 0. It's not. This one, okay, this one is going to return, okay, it's going to return 2, oops, sorry. It's going to return b times power of 2, 1. Okay. And then this one, I'm running out of board space. This one is going to return, I'll just use POW, pow of b, whoops, I did it again. Return b times power of 1, 1. And then this one is going to return, whoops, yeah, this one is going to return b times power of 2, 1, 2, 0, like that. Okay? And then that one's going to say, oh, I'm 0, returns 1. So this final one is going to return 1. Look at what, let's go backwards now. This one returns 1. Okay? This one returns b times 1, which in this case is 2, I guess. I should just replace these all with 2. But anyway, 2 times 1. Okay? And then this one's going to return, and that's going to be here. And this one's going to return 2 times 2. And this one's going to return, whoops, I missed one. I did one extra, sorry. This one's going to return 2 times 2, 2 times 2 times 2 times 2, which is 4, and then 2 times 2 times 2, which is 8. Okay, so you're going to go backwards up the chain. And then finally, the one that you originally called, okay, the one that we originally called up here returns 8. Okay? That's how that actually works. You got to go through all these things. Sorry, I had one extra one down there, I believe. Okay? But you're going to walk it through that way if you want to figure out exactly what's happening each time. Okay? All right. So that's how we do recursion for something like the power function. Okay? Factorial, I'm going to skip factorial. It's going to be exactly the same thing. More or less exactly the same thing. Factorial is when you do like 5 factorial. You guys know this from math class, right? That's 5 times 4 times 3 times 2 times 1. Notice it's very similar in form, right? You're going to do this times factorial of 1 minus this number. This is this times factorial of 1 minus that, et cetera, down the line. Okay? All right. Let's go through. We've got 10 minutes. Might not quite finish it. Let's look at one other example. When you guys in Comp 11 did recursion, did you do Fibonacci numbers? Oh, half people are going no. The other half people are going yes. Might have been a different teacher. You did it earlier. Let me go through that real quickly here and show you why sometimes these are very, very inefficient, and you would not want to do these this way at all. Okay? You will still get the right answer. Oops, still get the right answer, but it will be very inefficient. Okay? All right. All right. So here's what a Fibonacci number is. Okay? Fibonacci numbers, they happen a lot in nature, and they are basically it's a sequence of numbers. Okay, it starts out with 0 and then 1. Some people start out with 1 and 1. It depends on what your math flavor is that you came from. But 0 and 1, and then all you do is you add the 2 previous numbers together, and you get the next integer in the sequence. And you add the 2 there, and you get 2. And you add the previous 2, and you get 3. And you add the previous 2, and you get 5, and you add, et cetera. Right? That's what the Fibonacci sequence is. Okay? And we can write that in kind of a mathy way like we did before. Okay? We can say that the Fibonacci number n, and this is 0, 1, 2, 3, 4, and 5, okay, and 6, right? Fibonacci number of n equals the following. Okay, so that was a little better. Fibonacci n equals the following. 0 if n equals 0. 1 if n equals 1. Otherwise, it's going to be the Fibonacci number of n minus 1 plus the Fibonacci number of n minus 2. And that's if n is greater than 1. Now, let's look at what we've done here. We've now said that we've defined Fibonacci numbers in terms of other Fibonacci numbers. That's the recursion part of it here. Okay? We've said the Fibonacci number of n is going to be a Fibonacci number. It's going to be these special kind of base cases. There's actually 2 base cases in this case. Okay? Or it's equal to the Fibonacci number of n minus 1 plus the Fibonacci number of n minus 2. If this is n, 3, right, the Fibonacci number of 3 equals the Fibonacci number of n minus 1, which is 2, which is 1, plus the Fibonacci number of n minus 2, which is 1, also 1. 1 plus 1 is 2. Okay? Pretty straightforward, I hope, how that works. Okay. Because of this recursive definition here, we can actually do this recursively. Okay? We could say, let's say we want to do this. Int Fibonacci, and I'll just write fib, like I've done there, Fibonacci number, of some variable n. Okay? Okay, what it's going to do, it's going to return an integer, and you're going to give it an integer. Okay? And you're going to have your 2 base cases, first of all. You're going to say if n equals 0, return 0. Okay? If n equals 1, return 1. Okay? Otherwise, we're going to return Fibonacci of n minus 1 plus Fibonacci n minus 2. And we are done. Okay. Do people agree that that's a proper definition, or using the definition of Fibonacci, that would actually work to produce Fibonacci sequences? Okay, good. Maybe you talked about this in 11 or the other classes, or 50 as well. But what's the big, big problem with that? Yes?
For each number, you have to compare versus 0 and 1.
For each number, so you're saying that this is for each one you have to go through this twice? So how could we make that better?
You could see if n is greater than 1.
You could see if n is greater than 1, but remember, we're trying to return 1 if it's equal to 1 and 0 if it's different, right? So you'd want to do it, you would want to swap it. Okay, you could do that. That's one way of, that's one inefficiency in here. There is a much bigger inefficiency. Good idea. There's a much bigger inefficiency. Yes?
Every time you want to calculate every single previous number, so if you're calculating
Yeah, so the answer was each time you're doing each time you're calling this Fibonacci number, you're starting this kind of terrible expansion of calculations that you have to do. Notice every time you call this, you've got to call 2 of these guys. And then when you call this, you have to call 2 below this one. And for each one of those, you have to call 2, and then et cetera, et cetera. This is an exponential amount of extra work that you're doing. Besides the fact, right? That's besides the fact that you're calculating Fibonacci of n minus 1 and the Fibonacci of n minus 2. You're going to have to do that multiple times. You're going to have to calculate n minus 1 and the Fibonacci of n minus 2 a whole bunch of times, depending on how big this is. For a computer, a modern computer, it's almost impossible to get this function, or this step function, to do Fibonacci numbers greater than about n equals 20. Right? Because there's so much extra stuff going on that you've exploded the problem by trying to do this, right? If you thought the little diagrams before that were confusing, try doing the diagrams with this one, right? This one returns 2 different things. This one returns 2 different things. I mean, it gets ugly, right? So this is not a particularly good way of doing this. Okay? There is a better way of doing it. Okay? We've got about 5 minutes. I think I can get through at least the idea of what the better way of doing this is. We said that the problem with this is that we're redoing a bunch of work. Okay? We're redoing a bunch of work that we actually don't want to do and don't need to do. Why redo work if you've already calculated something? Okay? A much better way of doing this, okay, is actually, okay, I don't know if I guess I don't have it on here. A much better way of doing this is to say, instead of just passing in this value, also pass along the values that you can calculate at each step of the way based on where you already are in the process. Okay? And I don't actually have this here to write it out. I don't want to take the time to actually do it all out. But the basic idea is you're going to call the Fibonacci number and then use a helper application, okay, or sorry, a helper function to actually do some of that calculating where you're going to have something along the lines of this. Instead of just passing in n, you're going to pass in n, and you're also going to pass in, let's say, in this case, it's going to be prior 0 and prior 1 into that Fibonacci function. If you do it correctly, which I guess I'll get to on Wednesday, I'll do it right at the beginning of class. If you do this correctly, these two numbers will be able to pass on that information that you're losing by, or that you're having to recalculate in the other situations here. Okay? And when you do that, we'll find out that it's actually much, much more efficient to do it that way. It involves another function, but it makes it a lot more easy to actually do the calculations. Okay? All right, I think I'll stop there for right now. Any other questions on the homeworks, labs, recursion? Yes? You will not need to use recursion in either the homework or the lab. You can, though. The linked lists are they handle recursion very nicely. So you can if you want to. Yeah, but you don't have to. OK, good.